Well, hello, chemistry fans. Welcome to the YouTube video that we will walk our way through the rest of this chapter. There'll be one or two videos. We'll see what we can accomplish, I guess, about an hour each one. And this is continuing on what we were talking about on Wednesday's lecture. So we had just talked about electronegativity, polar covalent bonds versus ionic bonds. And now we're going one step further and talking about Lewis structures. So sometimes you'll see it in textbooks as electron dot structures, but I most likely will always refer to these as Lewis structures. Okay, and it's really just placing the dots around atoms in molecules, and it's indicating how the valence electrons are distributed in a molecule. Okay, and so if two hydrogen atoms come together, each of those atoms have one electron. So just remember these are 1s electrons. Okay, and when they both come together, they form a covalent bond. Okay, so this, drawn with the dots between them, is exactly the same as what we have showed in lecture. Okay, this line here indicates the of two dots or two electrons between those two atoms. Okay, so a little fancy picture, I guess, is the two atoms with the two electrons shared between them. Okay, so what we can do is talk about different groups. So hydrogen has one electron per atom. If we move on to, let's say, boron, okay. So looking at the group numbers, you would expect boron to have 3 electrons. So 3 valence electrons. Okay, so that has 3 valence electrons. So we could draw boron as just really this with 3 dots around it. Okay, and so this is saying that boron would like to form 3 bonds. Okay, because if you combine this with hydrogens, okay, you're going to get overlap. Actually, let me get this plus out of the way. You're just going to get overlap with these 2 electrons. Okay, so you can form a hydrogen bond there, and one here. Okay, and so however many dots you have around an atomic symbol, that will generally tell you how many bonds it likes to form. Okay, if they're single dots. And so let me show you another group. So carbon, for instance. Okay, so carbon has 4 valence electrons. Okay, so we can draw that as 4 dots. Okay, and so we know, for instance, that CH4, or methane, is a nice stable molecule, and we can indicate it. We'll talk about shapes later, but we can just indicate it as this, where you have 4 bonds. Okay, and again, you can say, this would bond to 4 hydrogens. Okay, where you have these as the separate lines. Okay, etc. All right, so what do you do if you continue to move your way across that group, and now you come up against the next one, so nitrogen. So nitrogen has 5 valence electrons. Okay, so we can draw that as 1, 2, 3, 4, 5. Okay, so now these are paired up. So they're not going to want to pair with anything else. So this is really saying nitrogen likes to form 3 bonds. So if you're just doing again with hydrogen or something, okay, we see that nitrogen forms 3 bonds. And an example of that is NH3, which is ammonia. Okay, which you can, draw in these line diagrams as that. Okay, so this is exactly the same as this one up here. Okay? All right, so what do you do for oxygen? Oxygen has 6 valence electrons. So to find out how many bonds it likes to form, let's do 1, 2, 3, 4, 5, 6. So if you're guessing that it likes to form 2 bonds, you are exactly right. Okay, so they're there. So this should be familiar to you. So this is actually water. Okay, and then you still have these dots around it like that. Okay, I guess I should have been explicit too and said those dots are still there. Okay. All right, so this is water, as you know. Okay, and it likes to form 2 bonds because you have, for oxygen, 2 unpaired electrons. So therefore 2 bonds. Okay. And then I guess the next group, so group 17, if we say, let's say chlorine or something like that, or fluorine. Okay, if you do these, they have 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. Same thing for this. Okay, and this is why, for instance, HCl or HF are popular or common. Okay, so with hydrogen, you just have 1 bond. Okay, so they like to form 1 bond because you have 1 unpaired electron. Okay, so these are not really, we're not really into Lewis structures yet and the whole steps of how to draw Lewis structure, but what we're really doing is talking about groups, okay? And so, again, if you have group 3, it likes to form 3 bonds. Group 4, it likes to form 4. And then that's kind of the maximum. And then after that, you go down to the group, whoops, these are 13, 14, 15, 16, and 17. Okay, so the group 15 likes to form 3 bonds, 2 bonds, and only 1 bond. Okay, so let's go back to the presentation here. So these are just another look at it. So if you have 2 fluorines combining, okay, each of the fluorines have 1 unpaired electron, so you can form just a single bond. Okay, so these s electrons, just think of those as you have 1 electron for each of the fluorines, and they just overlap to form this bond, the covalent bond. Okay. What is worthwhile noting here is that each of the fluorines are surrounded by 8 valence electrons. So if you count, for instance, we'll look at this fluorine first. Okay, you have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's surrounded by 8 electrons. This one will also be surrounded by 8. Okay, and we call that the Octet Rule that we'll see in a slide or 2. Okay, for oxygen, if 2 oxygens combine, I showed you what happens if oxygen combines with a hydrogen. Okay, but what if 2 oxygens come together? Well, you can form 1 bond, and then you still have unpaired electrons, right? So those can overlap as well. And so you end up with a double bond. Okay. If you have 2 nitrogens combining, you can get overlap of these 2, and those, and so you get a triple bond. Okay. So basically, anytime you have anything that has an electron, an unpaired electron, they can overlap to form a bond. Okay? And if there's any left over, see here there isn't, or here there is for an oxygen, but there isn't any left over for fluorine. So that's pretty well all that it can bond with this fluorine, but it could come in and do another bond with another fluorine here, for instance. Okay, so it could do an OF2 or an OH2, okay, type of bonding. All right, so the octet rule, we will talk about the octet rule. So what has to be surrounded by 8 electrons? These are really the only atoms that have to be surrounded by 8. Carbon, nitrogen, oxygen, fluorine. Okay, so these 4 in the Lewis structure have to be surrounded by 8 electrons. Okay, so this is the octet rule. Okay, and they must. Okay, this is, they absolutely have to. They can't have less than an octet, and they can't have more than an octet. Okay, so now looking at those that I didn't circle, this group here, okay, so the group 13s will most often have less than 8 electrons. Okay, so we sometimes call that the electron deficient group. Okay, so in their Lewis structures, we'll see that they're totally happy most of the time with only 6 electrons around them. Okay, they can have 8. Okay, so they can have an octet, but oftentimes they'll have less than 8. Okay, and that leaves then all of these guys. So everything we haven't talked about yet. So in groups, okay, so let's just say in the 3rd period and lower, they can have more than 8. Okay, so they may have, okay, so this group, we'll just say they may have an octet, but they also can have more than 8. Okay, and the reason for that, I guess the hand-waving explanation, there's a more sophisticated way when you get into sort of quantum mechanical bond theory. It's not as simple as this, but just think of it as their orbitals are larger, okay, so they could accommodate more bonded electrons. Okay, so if you have a larger orbitals that are involved in bonding, you won't have electron-electron repulsions with added electrons. Okay, so they can just take more than 8. All right, so let's look at the steps for determining or drawing a Lewis structure for a molecule. And the first thing you're going to do is, whoop, I don't know what this is doing here. Okay, PowerPoint. I think I just lost my internet. The first thing you're going to do is you are going to determine the number of valence electrons. Okay, start a new page. Wow, I lost everything. Okay, so you are going to determine the number of valence electrons. Okay, so the total number of valence electrons for all atoms in the molecule. Okay, and if you have a negative charge, then you're going to, so a negative charge, you're going to add 1 electron. If you have a positive charge, then you're going to subtract 1 electron. And so let me just show you how easy this first step is. So if we have this molecule, you're just going to add up the valence electrons that carbon has and 4 hydrogens have. So carbon has 4 valence electrons. Hydrogen has 1. Okay, but you have 4 hydrogens. Okay, so you're going to have a total of 8 valence electrons for this molecule, right? So, so 4 for this carbon and 4 times 1 for all the hydrogens, okay? For positive charged species, so something that we're going to draw a little bit later, how about this one? So H3O plus. Okay, if it has a plus charge, you're going to subtract an electron from that total. So we've got oxygen has 6 valence electrons. Hydrogen has 1 valence electron, but you have 3 of them. Okay, so that's a total of 3. So far, you have 9 valence electrons, but it's a positive charge, so that means you've lost an electron. Okay, so let's subtract 1 valence electron. So that gives a total of 8 valence electrons for this H3O+. Okay, if you have this one, CO3 2-, you have, so carbon has 4 valence electrons, oxygen has 6 valence electrons, but you have 3 of them. Okay, so that's 18 valence electrons. And this means you have added, instead of losing, you've now added 2 electrons. So let's add another 2 to that total. So that's a total of 24 valence electrons. Okay, so that's all we mean by this first step of just counting the number of valence electrons. Okay, so step 2 is then connecting the atoms. Okay, so you're just going to draw lines between all the atoms in the molecule, and hydrogen and the group 17s will only form 1 bond. Okay, and elements in the second row will form a certain number of bonds based on the columns they occupy. Okay, and so we already went through that, right? So, you know, so groups 13, 14, 15, 16, 17. So this is 3 bonds, 4, 3, 2, and 1. Okay, so just what we talked about before. Okay, oh, I guess here's a table of that. Okay, so 3 valence electrons, so I don't like these A's, whatever, so this is the groups that we talked about in class. Okay, group 18. Okay, so if you have 3 valence electrons, you form 3 bonds, 4, you form 4, but as soon as you have 5 valence electrons, now you go to 3, 2 bonds, 1 bond, and if it's a noble gas, it doesn't form any bonds. Okay, so it's just stable by itself. Okay. All right, so this is, you know, the same as what was on the previous slide. This is the rule I was talking about. If it is in the 3rd row and lower, you often have a central atom that has more bonds than predicted by the octet rule. Okay, and so the octet rule is saying really the maximum number of bonds you can form are 4, right? Because each of these contains 2 electrons, and so if we have 2, 3, 4, 5, 6, 7, 8, the carbon has 8 electrons around it, or an octet. Okay, but you can have something like, let's say PCl5, okay, that has a phosphorus surrounded by 5 things, okay, or 5 chlorides, I guess to be precise. And so now you have 1, 2, 3, 4, 5 bonds, each giving 2 electrons. So the phosphorus is actually surrounded by 10 electrons. Okay, so phosphorus is in the 3rd period or the third row, and so that's totally fine. Okay, if you try to do that with this, with nitrogen, it's not going to happen. Okay, because nitrogen is in that group that absolutely has to have an octet. Okay, so once you have the bonds, you're going to just put all the electrons that remain as dots around all the terminal or the periphery atoms. Okay, except for hydrogen. So hydrogen is totally happy being surrounded by 2 electrons. Okay, so for instance, if we look at a hydrogen-hydrogen bond, okay, this is totally happy as H2, and notice that each of the hydrogens are only surrounded by 2 electrons. Okay, and it's totally fine because the only orbital that hydrogen can use for bonding is the 1s, which has a maximum of 2 electrons. Okay, so it can't get to an octet. Okay, the only reason why, why is the octet so important is, if you look at nitrogen, you've got the 2s and 2p orbitals. So this can accommodate 2 electrons. This can accommodate a total of 6 electrons. So that's where your 8 comes from. Okay, so all the orbitals being filled, and you have a maximum of 8 electrons. All right, and if you have any electrons remaining after that last step, then they go on the central atom. Okay, so we're going to go through tons of examples of these, and so you'll see what I mean by that. Okay, and if no unassigned electrons remain, then you're going to form multiple bonds. Okay, either a double or a triple bond. Okay, so write down those steps and be familiar with the steps in drawing Lewis structures. But we're going to go through a bunch of examples, and I'll walk you through all of these different steps for different types of molecules. And so the first one I want to do is water. Let's do the Lewis structure for water. This first step says, okay, how many total valence electrons do you have? Well, we've got 6 from the oxygen and 2 for the 2 hydrogens. Okay, so a total of 8 valence electrons. Okay, so what you do first is you just draw lines, okay, joining the 2 atoms. Okay, and so far we've placed 2 electrons and another 2. So we've placed a total of 4 electrons, but we want to get to 8. So they go, you can't go around the hydrogens, okay, because hydrogens can only have 2 around them. So the only one that's left, so we still have 4 electrons, they go in the central atom. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is the Lewis structure. So Lewis structure for water is that. Okay, so now we have placed 1, 2, 3, 4, 5, 6, 7, 8 electrons in total. Okay, I guess I shouldn't put these dots to confuse with additional. There we go. Okay. All right, let's move on to, how about this one, CCl4, carbon tetrachloride. The number of valence electrons, we have 4 for the carbon, and then we have 28 electrons from the 4 chlorines. Okay, so each of these are 7 valence electrons, but we have 4 of them, so 28. So that is 32 valence electrons in total. Okay, so just draw bonds to the chlorines. So we've now placed 8 electrons, okay, 2 in each of these lines. So 8, and now you start building up on the periphery. So we've got 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 6, 7, 2, 8, 9, 30, 31, 32. Okay, so we don't have any left over, so no dots go on the central atom. So this is the Lewis structure for CCl4. Okay. What about this one, NH3 or ammonia? So we have 5 valence electrons from the nitrogen, another 3 from the 3 hydrogens. So total of 8 valence electrons again. So let's just do this. Okay, again, we don't build up additional electrons around the hydrogens. They're totally stable right now. So we've placed 6. So we just have 2 more to place, and that goes in the central atom. So they go just like that. Okay, so this is the Lewis structure for ammonia, NH3. Okay, so here's a little more challenging one. CH2O. And if I were to put an example like this on the midterm, I would be explicit. You know, a lot of examples, you know which is the central atom, so I don't have to tell you nitrogen is the central atom in this one, for instance. But in something like this, it's not really clear. Is the oxygen the central? Is it carbon? So I'll be explicit and say that carbon is the central atom. Okay? And so let's do, you know, number of total valence electrons. So carbon has 4. Okay? Hydrogens, you have 2 because you have 2 hydrogens. And then oxygen has 6. So 12 valence electrons in total. So carbon is the middle. So let's put 2 hydrogens and then an oxygen. So let's just do it like this first. Okay. So we've joined an oxygen, 2 hydrogens. So we've now placed 1, 2, 3, 4, 5, 6. So let's build up around the outside. Hydrogen is cool, but let's do around the oxygen. So we've got 6, 7, 8, 9, 10, 11, 12. Okay, so we've now placed 12 valence electrons, but hopefully you can see the carbon has only 2, 3, 4, 5, 6 electrons, so it doesn't have an octet. Okay, so if you're at the place where you have a structure like this, everything is built up, you don't have any lone pairs or dots left on the central atom, and so your central atom has less than an octet, what the strategy is, if I just get rid of all the scribblings here, oh, it's going to take forever. There we go. What you do is you move 2 electrons from here to there to form a double bond. Okay, so you can redraw this as, okay, you keep the same 2 dots or 2 pairs here and the bonding to hydrogens. Okay, and now that is a preferred structure because carbon now is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. Oxygen surrounded by 1, 2, 3, 4, 5, 6, 7, 8. Or whoop, 1, 2, 3, 4, 5, 6, 7, 8. If I could only count. Okay, so oxygen has an octet. Carbon has an octet. Hydrogens have 2 electrons, so that's good for them. Okay, so everything is nice and happy. Okay. All right, what about this one? SF6. So looking at total number of valence electrons, we've got 6 from the sulfur, And then we've got 42 from 7 electrons, 7 valence electrons for each of the fluorines, but you've got 6 of them. Okay. And so that's a total of 48 valence electrons. Okay, so let's do the 6 bonds here. All right, so we've placed now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons around the sulfur. Okay, and if you look at the periodic table, sulfur is actually okay with that. Okay, so it has, it's in that 3rd row and beyond, and so it can have more than 8. Okay, you can have sulfur that has just 8. So sulfur can form a compound SF4 where it has an octet, but with this particular molecule, you have more than an octet, and sulfur is able to accommodate it. So this is fine. Okay, so we placed 12 electrons, so let's build up around the outside. 13, 14, 15, 16, 17, 18, 20, 24, 29, 30, 32, 33, 34, 35, 36, 42, 43, 44, 45, 46, 47, 48. So this is the Lewis structure for SF6. Okay, again, no additional electrons left over. Now, if it was this, SF6 2-, after you've built up all these electrons on the outside, you'd still have 2 left, right? Because this means you have to add 2 more electrons, so that makes it 50 valence electrons. So those additional 2 would go on the middle central atom. Okay, so again, once you're done building up all around the outside, whatever's left to get to the total you need, they have to go around that central atom. Okay, let's look at ICl3. Okay, so this, you've got 7 valence electrons from the iodine, and 7 times 3, so 21 electrons from the 3 chlorines. Okay, so 28 valence electrons. So let's just draw lines here. So we've placed 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22, 23, 24. So now we've gone all around the outside. They now have to go around the central atom. So 24, 25, 26, 27, 28. So we actually have 4 valence electrons that go around the center. Okay, and we call these lone pairs. Okay, so these things where you have 2 dots that are kind of just sitting there, those are called lone pairs. Okay. All right. Let's look at another one, and this is ozone. And this is an interesting example. So if you look at valence electrons, we've got 6 for each of the oxygens. We have 3 of them, so that's 18 valence electrons. Okay, so let's just connect the oxygens. Okay, and so we've got 1, 2, 3, 4. Let's go around the outside. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 around the center. Okay, so this is a good kind of first run through it. But looking at this, oxygen has to absolutely have an octet, and these ones do. Okay, so these ones have an octet. But this one only has 2, 4, 5, 6 electrons around it. And so it's got less than an octet. And so our strategy then is to promote electrons to form a double bond. So we can rewrite this as this. Okay? And so this is one example. But what if I decided, instead of on the left side, what if I decided to do this? Okay? So you could have also this one. Okay? And so the way we normally indicate this, if it's kind of your choice whether you make the double bond on the left or the right, or different combinations, we call these resonance structures or resonance forms. Okay, and the way we normally indicate that is we just say with a double arrow, okay, that it either could be this one or this one. Okay, and the actual bond is somewhere between a single and a double bond. Okay, and so sometimes we'll write the overall structure as this, which indicates that these bonds are sort of between a single or a double bond. Okay, both of these examples. Okay, and so that's just really saying that, you know, the oxygens, you know, in this resonance form, these two oxygens are bonded just with a single, but in this resonance form, you have a double bond. Okay. All right. So, what about an example like this? Okay, another one with resonance. And so we've got 4 electrons for the carbon, and then we've got 18 electrons from the 6 oxygens, and then we have another 2, right, from this negative charge. Okay, so that is 8, 9, 10, 14, so I guess 24 valence electrons. Okay. And so let's draw the structure. So carbon, and then let's draw the 3 oxygens. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so what's wrong with the structure? Carbon doesn't have an octet. So let's do a double bond. And so let's get rid of these ones and move it there. Okay? But I could have also done them over here, right? So I could have also drawn it like this with all the dots around it. Okay. Or I could have also drawn it like this. Okay, so this one has 3 resonance forms. Okay, because the double bond can switch places between this one, and that one. Okay, and so you'll see this very typically with, you know, these kinds of structures, with nitrogens with oxygens, sulfur with oxygens, okay, especially the anion species of these, you know, like nitrate, for instance, sulfate, okay, sulfite. Okay, so you'll see these different resonance forms. You know, we already looked at carbonate. Okay, you'll see these resonance forms with these types of structures. Okay, so I have in the slides, if you want to take time, I worked them out for you. These are just kind of taking you through the different steps, okay? The ones that I just worked out for you, okay? And so this is a resonance form where the double bond can go in either direction, okay? All right, let's talk about formal charges. Okay, if we have this structure, let's say, and I want to know what are the charges at each of these atoms. The textbook or the PowerPoint gives kind of a different formula for this. The easy way for formal charge is just, if you want it for, let's say, a particular atom, just put down its number of valence electrons. Okay, and then subtract the number of bonds that emanate from that. And then subtract from that how many individual electrons surround that atom. Okay, if any. Okay, so maybe you will have 0 there if there are no additional electrons. And so let me show you what I mean. So the formal charge for this carbon is its number of valence electrons, so that's 4, minus the number of bonds that emanate. Well, you've got 1, 2, 3, 4. And then additional electrons, you don't have any around the carbon, so that's just 0. So that's a formal charge of 0. For this oxygen here, its valence is 6, minus 1 bond, minus 1, 2, 3, 4, 5, 6 electrons. So that gives you a -1 formal charge. Okay, and you'll see that this one is symmetrical, this oxygen, and so this will also be a -1 charge. And then what about this oxygen here? You've got 6 minus 1, 2 bonds, minus 1, 2, 3, 4 electrons, so that's a formal charge of 0. Okay? So a pretty important rule is a Lewis structure will be the most stable when the formal charges of the individual atoms are 0 or plus or minus 1. So if at all possible, try to get the formal charges by using double bonds, for instance, to get everything to 0. But if you're not able to, plus or minus 1 is cool, right? Just like we saw here. So we had 2 atoms that had a -1 formal charge, and that was fine. The rest were zeros, okay? But if you ever get a formal charge where you have some atom where it's +2 or -2 or -3 or something, there's a better choice for a Lewis structure, okay? And so what's a example for that? Let's see. So what about let's do nitrate. See what that works out to here. Okay. So nitrate, you have 18 valence electrons for the 3 oxygens. You have 5 for the nitrogen, and then an additional 1 for the negative charge. Okay, so that's 24 valence electrons. So let's do this. So we've got 6, 7, 8, 9, 10, 11, 12, 14, 18, 19, 20, 22, 23, 24. Okay, so here we recognize that nitrogen doesn't have an octet, okay? But if you kind of forget that and are looking at, if this is a good structure or not, look at the formal charges. So what is the formal charge in the nitrogen? Well, it's its valence electrons is 5 minus 3 bonds emanating from it, and then you don't have any dots around it. So that gives you a formal charge of +2. Okay, so that's more than plus or minus 1, so there's no way that that can be stable. Okay, and so this structure, if we do this, okay, where we do a double bond like that, okay. Now, let's look if that's any better. Okay, so the nitrogens now have, the nitrogen has an octet around it, okay, and all the oxygens have an octet. And so if we look at formal charges, this oxygen would have a 6 minus 2 bonds minus 4 dots. Okay, so that's a formal charge of 0. These oxygens are the same surrounding it, so those will be both, or each, 6 minus 1 bond, and then you have 1, 2, 3, 4, 5, 6 dots. So it's going to be minus 1. And the nitrogen this time will be 5 minus 4 bonds, and then you don't have any, so that's a +1. Okay, so the formal charges here are such where it actually is okay. Okay, you just have formal charges of plus or minus 1. Okay. All right. There is another example. So what if you were to do this? So instead of just one double bond, what if you were to do the Lewis structure like this for NO3 minus? So you're probably wondering this, right? Okay, so all I've done is, I've now maybe moved these electrons up to there. Okay, so now you have 2 double bonds. Okay, if you look at formal charges, this oxygen, that'll have a 0 formal charge, this will have a 0, this will have a -1, and the nitrogen is going to be 5 minus 1, 2, 3, 4, 5. So that's going to be 0. So by formal charges, this looks pretty cool, but nitrogen can't have more than 8 electrons, and nitrogen here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So there's no way that you could do this. Okay, so you're just going to stick with this structure. Okay, so the nitrate will just have 1 double bond. Okay, like this, and we should always indicate that that double bond can move around, right? So it can be this one, okay, with all the dots around it, etc. Okay. Or it could be this one, okay, where the double bond is, where haven't I put it yet? Down like this. Okay, and then again, all the lone pairs around everything else, like that guy. Okay, so nitrate has 3 resonance forms as well, okay, but only 1 double bond. Okay. All right, so I think that is a great place to stop for this video, give you a little break. So the next video, we will talk about how to take those Lewis structures and then figure out what its shape is. So what's the molecular shape? And that's just taking one more step beyond the Lewis structures. So I will see you in the next video.